So, yeah, returning the homework folders. This week, exam, reminder, it's covering the first 3 chapters. So 21, 22, 23, doesn't cover capacitors. But in class, of course, we continue. There will be, there's no homework help session tonight, but there will be help/review sessions run by the CAs. Either tomorrow night or Wednesday night. I will send an email about that, so look for the email. Practice exam was put up last week, solution went up today. No quiz, no homework this week. Yeah. All right, any questions before we dive back into capacitors? No? Okay. All right, so last time we talked about capacitance. The 2 most important things we learned were the sort of fundamental equation for capacitance, which is Q equals C delta V. All of these are magnitudes. They're all positive. We learned that for a parallel plate capacitor, we have epsilon naught A over D as capacitance. And we learned that inserting, or rather, let me say, filling the space between capacitor plates the dielectric increases capacitance. So your new capacitance will be kappa times your old capacitance. And kappa here is the dielectric constant. Yes. Oh, this. I see. A little bit more. Okay. Sorry. Yes. Didn't hit you on the head, right? No, you did. Oh, question. Yeah. What is the subscript for the capacitance? Oh, I just said C nu equals kappa times C ohm. Yep. So it's the Greek letter kappa, and it is particular to different materials have different dielectric constants, and yeah, it basically represents by how much capacitance increases, or another way of thinking about it is by how much the electric field in the region decreases. So when you put a insulator, a dielectric material between the plates, it decreases the electric field between the plates, and that has the effect of increasing the capacitance. Yes?
And what a dielectric is?
It's just an insulating material. Other questions? No. Okay. So today we're going to talk about combining capacitors. And there are many ways of combining capacitors. 2 of them are special. Okay, but let me be clear. So hopefully you've already heard or seen in your reading or watching videos, two ways of combining capacitors are series and parallel. But let me be clear, that doesn't mean that every case falls into those two. There are plenty which are neither. Okay, these two are special simply because they can be simplified. Right? There are plenty that cannot be simplified, and we have other tools for handling those. Okay. Right. So series. You have two capacitors in series, C1 and C2. The important things to know here, Q will be the same. All right, which makes sense because since there's only one wire connecting them, whatever charge flows in gets plus Q over here, you get minus Q over here. But you can see that this middle portion is actually physically detached. So if you get minus Q over here, then you have to get plus Q over here, and then minus Q over here. So it would be the same Q for both of them. Okay. Voltage delta V does not have to be the same. It might end up being by accident, but it doesn't have to be. And if we want to replace these two with a single effective capacitance or equivalent capacitance. So you'll sometimes see this written as C equivalent, CEQ, or C effective. So how do we, what helps us replace these? It turns out to be 1 over C equivalent equals 1 over C1 plus 1 over C2. Now, the reason for this is when we replace these, right? So this one, let's say, has a voltage delta V1. This has a voltage delta V2. If we replace these with a single one, is that a question or you?
Yeah.
Okay.
I thought that was for in parallel.
No, you're thinking of resistors.
Oh,
Another question? Okay. So yeah, if you're replacing these with a single one, that means you don't want the rest of the circuit to be affected. Okay, so we have Q1 delta V1, C1 delta V2, Q2, C2. We already know that Q1 equals Q2, so that will have to be the same as the Q equivalent over here. We also want that when we replace these two with a single one, it shouldn't have an effect on the voltages in the rest of the circuit. So we should have delta V1 plus delta V2 equals delta V equivalent. Does that make sense? Right. We don't want to disturb the rest of the circuit. We just want to replace those two with an equivalent capacitance. And so the potential drop should stay the same in total. And we have delta V1 plus delta V2 equals this. However, we know from our fundamental equation for capacitors, delta V is Q over C. So I could write this as Q1 over C1 plus Q2 over C2 equals Q equivalent over C equivalent. But I know that Q1 is Q2 is Q equivalent, so I can just cancel out all those Qs, and that's how I end up with this equation. Take a moment to absorb, ask questions, and if any of the steps are okay. After this step, I'm just saying, cancel the equal Qs. Yes.
So we know the change in potential when you add the two capacitors together is equal to whatever equivalent larger capacitor, and potential is equal to charge over
Capacitance.
And then we can simplify that to the first
Yeah.
thing.
Yes.
I was not having a 2Q charge on the single capacitor when you're
Oh, because that would mean that, think of it in terms of charge that comes in and charge that comes out. All right, so you have plus Q coming in here, stuff happens in the middle, and plus Q leaving here, right, leaving behind a minus Q on this. So you need to have the same effect over here. If plus Q comes in, plus Q has to come out. Yes.
Does the effective, like the bottom, like equivalent capacitor, does that have half the capacitance? It has twice the capacitance of C1 by itself.
Oh, you're assuming that C1 is equal to C,
Yes.
which it doesn't have to be,
Oh, crap.
right? I mean, like you could have, maybe this is 2 microfarad, this is 3 microfarad, right? So then you would do, 1/2 plus 1/3 is 5/6, and then flip it to get, okay, C equivalent will be 1.2 microfarads. But you bring up an interesting point. So what will happen then is C equivalent will be smaller than C1 or C2. Okay, it will always be smaller than the smallest of these. Oh, yes. Yes, then individually. Yeah, so, well, I mean, you can use this formula to figure out how it relates to the combination. But yeah, I mean, like if you have, what I mean is that if you have like, we can extend this, it doesn't have to be just 2, right? You could have many of them in series. So supposing you had like, 10 microfarad, 10 microfarad, 10 microfarad, and then 2 microfarads, right? The equivalent one will have a number less than 2. Yes.
So does that mean in every case, the effective capacitor in parallel will store less charge than just one of the capacitors by itself?
But do you mean series?
And yeah, for series.
It will store less charge. No, I mean, it has the same amount of.
Or just one of the capacitors by itself, like C1 or C2, the effective one will store less charge than one of those by itself in a
I see. If connected to the same voltage for delta V, and then let's see, lower. Yes, that's correct. Yes.
Okay.
Yes. Other questions? Okay. So this is how you can combine capacitors in series. The other case is combining them if they are in parallel. C1, C2, and again we'll have Q1, Q2, delta V2, delta V1, and then again you're replacing it with a single equivalent capacitance, V equivalent, Q equivalent. So now the thing that they have in common is that delta V is the same. So we have delta V1 equals delta V2 equals delta V equivalent. And in terms of charge, again, we have that restriction that Christian has brought up. You want that, whatever charge comes in and goes out over here should be the same over here. So here, whatever charge comes in on this wire splits up into Q1 and Q2, right? So that tells us that, okay, Q equivalent has to equal Q1 plus Q2. So that, for total amount of charge going in here has to be the same as the total amount of charge. All right, and again, I can use this to figure out the equivalent capacitance. Again, I know the fundamental equation is Q equals C delta V, so this becomes C equivalent delta V equivalent equals C1 delta V1 plus C2 delta V2. But I know that all the delta V's are the same in this case, so I can cancel them out. So I get C equivalent equals C1 plus C2. This is for parallel capacitance. This one was for series. Oh, question, yes.
In a situation like this, what determines which wire out of the wire gets more charge?
Which side of the wire? Oh, it depends on the capacitance.
Okay, so the capacitors will influence the charge.
Yes.
That goes from, okay.
How it splits, yes, yeah.
Gotcha.
So they have the same delta V, right?
Yeah,
And so, so we can say, oh, delta V1 equals delta V2, but delta V is equal to Q over C. So this is Q1 over C1 equals Q2 over C2, which you can rearrange to Q1 over Q2 equals C1 over C2. So the bigger the capacitance, the bigger the charge. Other question? All right. So often a lot of circuit problems and these terms, series and parallel, we'll see them again when we do resistors, inductors, so on. They're quite general. And it's always true, no matter what you're talking about, regardless of whether it's capacitors or resistors or whatever. If two circuit elements are in parallel, that means they have the same delta V. If two circuit elements are in series, that means they have the same current running through. What else? So how do we identify things that are in series or in parallel? Well, those are sort of the main criteria that, oh, things in parallel have to have the same delta V, things in series have to have the same current. So what breaks that? So, okay, I'm going to write on this board. I'm going to cover this up. Anyone need more time to, okay, a few more seconds to jot stuff down. Anything you need me to read out? Or? Okay, all right. So how do we? So here's an example of two things in series. What would make them stop being in series if I have a junction here? Right. We said that for things in series, the current has to be the same. So if there is another wire that comes in the middle, where current can either split and go off or a new current can come in, that will stop them being in series. Okay, so not in series. For parallel, people get confused with this a bit more often. So if two things are in parallel, what that means is that you should be able to go from, so let's call this the positive end, this the negative end. So for capacitors in parallel, you should be able to go from the positive to the positive and see only wire, right? So I'm crossing a junction here, but it's only wire, right? All only wire, and go from the negative to the negative and see only wire. Okay. It seems a little abstract, so we'll do a few example problems. Go ahead and get your table fixes out. Right now, this is yes in parallel. Okay. Well, okay, first we'll start with the potential difference question, and then we'll talk about parallel and series. Right, so here, this is not a capacitor. What is this? This is battery, yes. So we have a 1.5 volt battery and 2 wires connected to it. It's not a complete circuit. I'm asking about VB minus VA. I've labeled 5 different points. Yes.
So is like A connected to E or?
No, there's a break there. There's empty space. Unanimous for B. B is correct. There is 0 volts difference between A and B. So these are ideal wires. And in any case, there's no current flowing because it's not a complete circuit. So both points A and B will have the same potential. What that potential is sort of arbitrary. All we know is about the potential difference that the battery causes. So I could say that A is at 2 volts and B is also at 2 volts. And then C would be at 0.5 volts. Right? It's a bit of an arbitrary choice, but that's fine. You only ever measure potential differences. You never actually measure potential directly. All right. Let me ask this similar, but slightly different question. What is VE minus V? Oh, question. Yes.
Can you explain why A and B were two?
Sure. In the battery, the longer end is the positive one. So if I cross the battery going from positive to negative, I'm going to lose voltage. And this tells me how much voltage I'm losing. So I'll be losing 1.5. All right. So now let's try VE minus VA. Oh, question. Yes. True, there would be no current, but there can still be potential differences. So a battery maintains a potential difference even if there's no current flowing through. Let's check. So, that's something here. So we have E, we have A here, we have 1.5 volts. So what we're going to do is we're going to take a walk on the circuit. All right, and so if I say start at point E, okay, so I start at some potential VE. Right now I'm just going across wire, nothing changes. Now I cross the battery. I'm crossing it from negative to positive. So will I lose or gain voltage? I will gain voltage, right? So I'm going from negative to positive, I'm going to gain voltage, I'm going to gain 1.5 volts. And then eventually I reach A and no other changes happen in between. So this is equal to VA. Then I can just rearrange. I have VE minus VA equals minus 1.5. Question, right?
Can you start with VA?
Yes, absolutely. So if I start at VA, go here, I cross the battery, but now I'm going positive to negative, so I lose 1.5 volts. Then I reach E. Move VA over, so I have minus 1.5 volts equals VE minus V. Yes.
How does a multimeter measure potential difference?
Oh, good question. Multimeters actually, what they do is they have a high resistance in them, And they use the voltage to drive a current through the resistance, and then they measure how big the current is. Now, of course, the question is, how do they measure the current? So we'll talk about voltmeters and ammeters in a little bit. But no, that's a good question. Yes, how do your measuring instruments actually work? It's a good question. So yeah, multimeters usually they just convert everything into currents, and they usually measure the currents. You can have dedicated voltmeters that how they work is basically they have oh yeah, I only just learned about this the other day. In fact, it's kind of interesting. So they have these two metal plates. Yeah, one behind the other. Let's say, and sort of off center. And so the connections are made such that, oh, this connects to one terminal, this connects to the other terminal. And so if they are opposite charges, they will try to rotate and align, right? And there's a spring that, makes it hard for them to align. And so you just like, oh, okay, how far, how strong the spring is. So you can see, okay, how far do they turn to align? That tells you like something about how strong the attraction is. And that's related to the potential difference.
Yeah, so this makes sense, but why would you not start at VA if like delta V would be final answer?
Why would you not start at E?
Yeah, point A. E minus VA.
Oh, yeah. You can do it either way. So that's what we said. You could start at A, then cross, and then lose 1.5, right? And then reach E, and then just rearrange it to get BE minus BA equals. Okay. All right. So that was just some background on potentials, and also introducing this concept of taking a walk around the circuit. We'll be doing this later on when we learn about Kirchhoff's rules, or loop rule and so on. And yeah, this is just a version of that. All right, so here is your capacitor question. So a bunch of circuits. I'm asking how many of these have C1 and C2 in parallel? Yeah, I'm only asking about C1 and C2, are they in parallel? Right? Each circuit has a C1 and C2, right? So for each circuit, judge, oh, are they in parallel or not in parallel? And then count how many satisfy that criteria. All right, go ahead and discuss. I know this is so let's take them one by one. This one, top left. Yes, no, no. Okay. It's sort of clear that C1 and C2 are in series over there. What about this one? Yes, that is correct. Remember the criteria we came up with was that you have to go from positive to positive and see only wire, and negative to negative and see only wire. So here, yes, the positives are both connected, and then the negatives are both connected. Questions about this? No, still okay. All right. This one. No, why not? C3 gets in the way. Let me sort of lay that out a little bit. So we have capacitor, another capacitor, wire here. Okay, so this is C3, C2, and C1. Okay, so If charge comes in over here, this will be positive, this will be positive, negative, negative. Negative connects to the positive of the next one, this will be negative, and current comes out over here. I can go from the positive of C1 to the positive, sorry, positive of C1 to the positive of C2, no problem. But I can't go from the negative of C2 to the negative C1, seeing only wire. I have to go through C2. Okay. And so there would be a potential change over C3. So C1 and C2 don't have the same delta V. Yes.
Would you say that C2 is in parallel with like the equivalent of C1 and C3?
Yes, you can say that. Yes. C2 is in parallel with the combination of C1 and C3. Okay, so you could say that, oh, C1 and C3 are in series, right? Reduce that into an equivalent capacitance, and then that combo would be in parallel with C2. Questions? Yeah.
Would the like direction that the positive and negative of C3 is at, would that depend on how much charge is stored on C1 and C2? Because I feel like it could, if C1 was large enough, it could also have the negative could be, I mean, you could go from negative to negative to negative to positive in C1, C3.
No, because this is physically
Oh.
separate,
Oh, okay.
so it has to stay neutral. Yeah. Other questions? Okay, let's try this one. Yes, no? Yes, they are in parallel. In fact, all three are in parallel. Okay, so here I can do positive to positive and negative to negative. I can do that with C3 as well. So C1, C2, C3 all in parallel. If I wanted to find the equivalent resistance, not resistance, capacitance, I would just do C1 plus C3 plus C2. What about this one? No connection on this side for C1 and C2. They're connected on one side but not on the other. This one, yes, they are connected on both sides by just one. Question?
For the last one, it makes sense that they're in parallel, but
Yes.
would C3 and C4 have charges as well?
Yeah, they can have charges, and C3 and C4 would also be parallel. I mean, with each other. C3 and C4 would be parallel.
So in which direction does the current flow through that middle?
That I don't know. I have to have specific numbers for that. Yeah. Yes. Sorry, say again. Let's see. Oh, okay. So I mean, there might be an initial setup current, but yeah, it would go to zero fairly quickly. Because eventually both these points would reach the same potential, and then there's no reason for a current to flow through the wire. C1 and C2, yes, they will still be, you can consider them in parallel. So let me show how you could redraw this. You could, and this helps often with circuits, is redrawing them while keeping the connections the same. Right, so we have one, okay, C1, C2, C3, C4. I could redraw this as this. So C2, C1, C2, C4. So you can see that I've kept the connections the same. I've just stretched or shortened wires. Right. We have C1 and C2 in parallel, C3 and C4 in parallel. Those combinations are in series. Let me be clear though, this wire is not really this wire. What I've done is sort of, well, it's hard to explain, but I've shrunk some and expanded others. Yeah, but in the case, eventually when it reaches that there's no potential difference between these two points, that no current flows through here, you would have current flowing like that. Question.
I thought that once the capacitors reach their capacity, there'll be no current.
Sorry, yes, yeah, once they're fully charged, there's no current through this part of the circuit at all, yes. Okay, yeah, let's save the discussion about the current for concrete numbers when we have concrete numbers at resistances. But it's true that if a wire has if 2 points have the same potential, then there's no need for a current to flow through that, but we'll look at that in more detail later. Right now, we're just going to focus on the static case. All right, so have some practice with series and parallel. Let's try, yeah, let's try this first. Mostly for D, D is correct. The C, the trap you fell into was you have to remember to invert one last time at the end. So these two are in series, right? So you have 1/2 plus 1/4 is 3/4. Flip it to get C equivalent is 4/3, right? 1.33, and then that is in parallel with the 6 farad. So you have 6 plus 1.33 to get 7. Questions? No? Okay. Try. Well, this should be quick. All right, show me your votes. All right, yes, all 3 of them are in parallel, so they all have the same delta V. All right. Yes, let's try this. Simon.
So we know that charge equals compactness times H in volts.
Yep. Q
And
equals C delta V, yes.
so we can find that the charge on a 5F capacitor to
Yep.
be 60 coulombs.
Yes.
And we also know that capacitors in series share the same charge.
Yes.
And since 4F is in series with 5F, this charge will be the same.
Exactly, yes. So yeah, using Q equals C delta V, we can find 5 times 12 is 60 coulombs is the charge over here. And then, as I said, these 2 capacitors are in series, so they have the same charge. Questions? Okay. Last one for today. Show me your votes. Okay, still need a bit more time for some people. But let me just take you through it very quickly. So again, we know that the charge on the 5 volt, sorry, not 5 volt, 5 farad capacitor Q equals C delta V, so 60 coulombs still on the 5 farad capacitor. The combination of the 2 farad and 4 farad is in series with the 5 farad. So the combination of these two should have the same 60 coulombs. How much does each one get? Well, they are in parallel, right? The 2 farad and the 4 farad. So they have the same voltage. So the only thing that determines which one gets more charge is the capacitance. The bigger the capacitance, the more the charge. So they'll split it in a 2 to 4 ratio. So you have 20 farad on 20 coulombs on the 2 farad and 4 farad, 40 coulombs on the 4 farad for a total of 6. I'll end with a demo. So we'll be moving quickly from capacitance to resistance. And so I'll end with a little demo on resistance. Anyone know what this is? It's basically a jump start battery, like so you don't have to wait for another car to come around. You can jump start your own car. It's pretty convenient. Yeah, I've used one of these before. So obviously they can supply a decent amount of voltage. And so I'm just connecting it to a metal strip. And the thing to know about current and resistance is that when a current flows through a resistor, it gets hot really quickly, yes. And you can see that if I increase the length, it takes a little while longer. And the other strip, I'm not going to do the other strip right now. I'll probably repeat that next time. The other strip is a little bit thicker. So you can see that that also has an influence on how long it takes. All right, that's it.